All right, on to example 2 of the more challenging Newton's force and motion problems. So in this example here, we have a hockey player and they're pushing off the boards and then they go skating forward and eventually come to a stop. So I've done the hard work of drawing the wonderful looking picture there, artistic rendition. I have given a hint of 4 events, so we do have to state some events here. The first one being they push off the boards, okay? So you see that Newton's third law pair there. So if they push on the boards push on them, they can move. Event 2, they get to this other point of 0.704 meters. Then they've glided for a bit. And then at point 3, they begin braking. So they apply this little braking force here on the ground, and then the ground applies the braking force backwards on them. So another third law pair, and then of course our hockey player stops. So we just need to write out our given here. So what we know from the question is at event 1, we start from rest. We don't know what speed it reaches at event 2, but we do know that from event 2 to event 3, we have constant speed. And then we have V4, which is 0, comes to a stop. We have been given the displacement between events 1 and 2. So that's going to help with part of the question we're asked for. The time to which the hockey player is skating for 4 seconds is between events 2 and 3. So it reaches the point of 0.704, glides for constant speed for a little while, so it's 4 seconds, and then brakes. So the braking force, there's a lot of information here. The braking force is 38 newtons. The applied force from the beginning, we don't have to write applied, but that's fine. It's 130 newtons west. The braking force is also west, okay? And what are we looking for? So we're looking for the acceleration in event from the first part, so pushing off to the point of getting to constant speed. We're looking at the acceleration during the constant speed, hint, hint, part, and then the acceleration during braking and stopping. And then we're also asked to find the total distance that the hockey player travels. So that means we need delta D23 and delta D34. Wow, lots of information looking for here. So this will be challenging to get through, but we're going to get through it together. So here we go. So like I said in the tips, you might have to draw more than one interaction diagram and more than one force diagram for different situations. And that is the case here. So I'm going to draw the interaction diagram for events 1 to 2 first. Okay. And that is this. So the skaters are system. They're applying a force to the boards. They experience a normal force with the ice and a gravitational force with the earth. Okay, so that's from 1 to 2, and then from, so for the force diagram there, we're going to have the reaction force of the boards on the skater goes to the right because it's pushing them, and that's the direction they're accelerating, so that makes sense. The normal force and the gravitational force are balanced, and we have an acceleration to the right. So that's for events 1 to 2. Events 2 to 3, the skater moves at constant speed. So the skater has no external forces acting on them. There's miraculously no friction here. Okay, so we have our normal and our gravity. And that means our force diagram is simple. I know I'm going between capital N's and little n's for normal force, so I apologize, but it's neither here nor there. I'm not taking marks off for that. So no friction force or applied force, so it's just no acceleration. Oops, hint, hint. And then for events 3 to 4 is when the skater's braking. So the skater's still moving to the right, which means when I go to draw my, when I go to draw my braking force, that has to go to the, yes, you got it, to the left. Because if we're moving to the right and we're accelerating, if we're braking, that means we're slowing down. So my acceleration is backwards because I'm slowing down. Even though the motion, right? Motion's that way, net force is backwards, which means the object is slowing down. I forgot my interaction diagram, so let's draw that. My normal and my braking force comes from the ice, and my gravitational force comes from the earth. Okay, so that's what that looks like for events 3 to 4. Similarly to the diagrams, I'm going to draw the word description for each event, or for each interval of time. So from 1 to 2, the skater speeds up in the positive direction due to the applied force from the wall or the boards. From events 2 to 3, the skater moves at constant velocity in the positive direction. That, of course, is due to their inertia. They want to keep moving in the same direction unless an unbalanced force acts on them. You don't have to mention that here, but that is why. And then in events 3 to 4, the skater slows down in the positive direction. Due to braking force, which is opposite to the direction of motion. Our assumptions here are that the object is a point particle and it's a constant acceleration from 1 to 2 and from 3 to 4, and a constant velocity from 2 to 3. Okay. All right. So just like in all the other parts of the question, I'm going to break it down from different intervals. So intervals 1 to 2, what the heck are we trying to find again? The acceleration in each section. So, okay. So we're going to use our force diagram from events 1 to 2 to figure out our net force equation. This is in the x direction. The applied force acting on the skater. Oh, I didn't set a convention up here. I'm going to say that right and up is positive for all 3 scenarios. Okay. So the force acting on the object is the applied force. And that's the only force in the x direction. And then that's equal to the mass of the skater times the acceleration of the skater. And now we can rearrange this equation for A. So we have 130.0 newtons over 54.0 kilograms to give us 2.4 meters per second squared. That should be east. Okay. Okay, so that's the acceleration in the first portion. It's also asked us for the displacement. But it's been given in this part of the question, so we'll just state it there. That's from 1 to 2. So from 2 to 3, let's look at our force diagram again up here. In the x direction, we have nothing, so that equals 0. That means MA equals 0. That means A equals 0. So no acceleration. That makes sense because, well, it says it's moving at constant velocity. So we can find the distance that it travels in that time, or the displacement, using our constant velocity equation. But we don't know the speed at this point. So what we do need to know, we need to find v2, which is the speed it reaches after events 1 to 2. And that means we can go, I use the kinematics equation, v2 squared equals v1 squared plus 2ad, and then solve for v2. That's 0, this is 2.4, and then this is 0.704. I'm being sloppy not putting units in, but I know you guys will do better than me. And I get 1.84 meters per second. So the velocity from events 2 to 3, because we know that the velocity from events 2 to 3 is constant, we're going to use that velocity that we just found to find the displacement, because we know the time. We know it was 4 seconds that they were working. So that gives me 7.40 meters, also east. So d equals v times t, and then d is 7.4. For those of you who are larger writers than I am, I apologize for the space. Just keep some lined paper nearby so that you can, finish these questions if you run out of space. Okay, from events 3 to 4, our net force equation, we have the only force acting is in the negative direction, that's the braking force, and that's equal to MA. So that means we go A equals braking force over mass, and this is A from 3 to 4. This is different than A from 1 to 2 and from 2 to 3. So we're plugging this in, 38.0 newtons divided by 54.0 kilograms, and we get negative 0.7 meters per second squared. And that makes sense because my acceleration is opposite the direction of motion. If I'm moving in the eastward direction, then my acceleration here, because I'm slowing down, is negative, okay? We're going to use this equation again. We have to use v4 equals v3 plus 2a delta d. And rearrange for delta d 3, 4. v4 squared minus v3 squared over 2a. 0 squared minus, so we're going to use 1.84. Okay, so that's my velocity 3, so because this is from events 3 to 4, v3 is the same as v2, 1.84, over the acceleration times 2, and that gives me 2.42 meters in the eastward direction. Okay, and so total D, I'm going to do it over here because I've run out of space. So our total D is going to be 0.704 plus 7.40 plus 2.42. And those are all meters in eastward direction, giving me about 10.5 meters in the eastward direction. Okay? More or less with some rounding. Awesome. Pretty loaded question, I would say.